Our normal training program is a 2-day training program. It's 4 hours base of classroom and then a day of hands-on type instruction where we teach you how to pretty much diagnose and troubleshoot liquid cylinders all the way up to just short of welding on them and pulling a vacuum. I've now created this derivative of that program that just basically looks at the real basics of a liquid cylinder. Can we do the next slide, please, Marie? In this slide, it's just showing you the cross-sectional construction of a liquid cylinder. The figure on the left-hand side, you'll see that you have an inner vessel that holds the cryogenic liquids. That can be 350, 400 degrees below zero. You have the outer shell, it's just what you touch and see, and then in between is the annular space where the vacuum is that helps hold the insulating value of the cryogenic liquid to the ambient outside. And then you have the super insulation, and you have also some of the functioning elements with the tubing that's used to create the pressure builder in the gas. This is just showing you some of the basic components: the inner vessel, the annular space, the outer shell, we'll call it the top components that are used to operate the cylinder, and then the halo that's there. That's really a DOT design requirement to protect the upper components should anything fall onto the cylinder or the cylinder should fall over. Helps protect those components. The figures on the right-hand side are just some actual hardware that you can see. Bring some realization to that. The figure in the center is showing you the coils that are in between the inner vessel and the outer vessel. The pressure building coils are usually in the lower 12 to 15 inches of a cylinder. We'll talk about their function in the later slides. The other coils that are there are used for vaporization of gas. You can also see the fill line that's used for drawing liquid out. It's also used to fill the cylinder, and it has a guide on there that helps support and hold the float rod. The figure next one over, second one from the right, is going to show you that the neck, that is the only place where the inner vessel where the cryogenic liquid is connects to the outside of the cylinder. That's the only location where the inner vessel can connect to the outside, as I said. So next slide, please, Marie. I'm going to talk about DOT4L design a little bit. So you have the halo that we had talked about that protects the upper components. There's a vertical element that supports that halo design, and that what we refer to as the stanchion. Those support brackets on one of those, on every cylinder that's out there, will have a nameplate. That nameplate is going to have the DOT designation. The table at the bottom, you'll see the common ones that are in the United States. There's a few others that are out there. There's a 150, a 372, and there's like a 4 something. They're oddballs. They're really older designs, some of the older Lindy designs, but these are the common ones that are used and sold in the United States today. These DOT designations are going to determine the pressure ratings and the max relief valve settings that you can have on those DOT ratings. In the table, you'll see the DOT4L100, that's a primary liquid withdrawal, has a maximum service pressure, which is the maximum relief pressure of 110. Those last 3 digits of the DOT number are going to dictate that design. So you'll see the rupture rating, that is 2 times the DOT number. That's the inner vessel rupture pressure and PSI. So it'll be 200 PSI rupture rating. Then the service pressure, maximum relief pressure, is determined by the DOT number times 1.25, 25%, minus 15 PSI for the 14.7 PSI of the vacuum that you'd have on the annular space. And that derives you the maximum service pressure. So you'll see that there in that table. And that's a nice table to refer to. I'll show you the common pressure builder settings and the economizer settings. So, and another point that I want to make out is if that serial number is missing, the cylinder really technically can't be filled and put on a truck. Needs to be qualified through the manufacturer, through the OEM manufacturer, as to what the serial number is, so you can determine the pressure rating, etc., and then get it rename plated. Next slide, please, Marie. Here we're just going to talk about some basic cylinder types. The cylinder figures that you see on the left-hand side of the screen will show you what we call a foot ring design, such as the 160 to 180 to 200 liter design cylinders, and then you have the wheeled-based design. The writing on the right is going to really kind of go again about the DOT numbers and some common applications. You have the DOT 4L100. That's a liquid use, can be 22 to 100 PSI type applications. Medical application for a liquid cylinder could be used to transfill liquids into what we call like a liberator or smaller portable oxygen units, or a lot of other low pressure type liquid applications. The DOT 4L200 is a medium pressure gas use cylinder primarily. 125 PSI on the pressure builder and a 235 maximum on the safety. 292 is the heavy duty gas use, what we call a high pressure cylinder. 350 PSI is the top safety pressure on that. And then the 412 is what a lot of people refer to as like a laser sill, a common high pressure gas use, what we call a VHP, very high pressure gas use cylinder. Next slide, please, Marie. Talk a little bit about tara weights. I mean, on that nameplate that we had shown you in the previous slide, there will be a nameplate, a weight stamped on there. That is the dry weight of the cylinder. So, and that that cylinder weight should be pretty accurate when you throw it on a scale. Should be within a few pounds that you throw it on a scale. That drawing, or the photo I have on the lower left is a individual customer-owned cylinder who added these fork tubes to a square base cylinder, changed the tara weight by like 80 pounds. You can't fill that cylinder and technically put it on a truck. So you'd have to put that aside and get the tara weight stamp to match what the cylinder actually weighs. A point I want to make too is that for the exact same volume of cryogenic material, there is a significant weight difference depending on the gas type. So you see 201 liters of nitrogen weighs 359 pounds, but the exact same volume, 201 liters of argon, weighs 624 pounds. They have different densities. So that's going to affect your level control, and it's going to have a serious effect on the final weight going out the door. But for the same volume of gas, you will have different volumes based on DOT rating. So you have in the lower there on the right, you have a 240 liter Taylor-Wharton cylinder. A DOT 4L200 holds 382 pounds of nitrogen, whereas the exact same cylinder in a DOT 4L292, a higher pressure cylinder with a 350 PSI rating, will hold 359 pounds of nitrogen. Why I say that is it's a common troubleshooting thing where a customer says, hey, I had a customer XYZ that was delivering me my cylinders for my cryo sauna earlier, and they were delivering low pressure cylinders, and their cylinder lasted a lot longer. You're delivering me a DOT 4L292 with a 22 PSI relief valve on it, but it holds significantly less volume of nitrogen, and that would be the reason why. That volume of material is determined by the length of the vent tube, what we call a tricoque, full tricoque vent. That's a DOT design that will have that tube project inside the cylinder. Can we have the next slide, please, Marie? So this figure here, it's just showing you the reason for that is you need that room in that inner vessel to allow for the expansion of the liquid at the higher pressure. The higher the pressure, the more volume you need. Therefore, same size vessel, the less volume of liquid that you'll have. And that's, as I said earlier, is determined by the length of the tricock vent that would project inside the cylinder. Start getting into some of the more complexities of liquid cylinders. If you look at their fill chart tables, that is for the maximum PSI safety. You can legally overfill the cylinder, providing you have a lower pressure PSI relief valve on it when you put it on the truck. But to do that, you'd have to turn the tricock vent off and fill above the tricock level. And you can refer to the manufacturer's fill charts for that. I also wanted to point out that liquid cylinders are going to be heavy. Next slide, please, Marie. You know, this is just showing you some of the common practices for handling cylinders. Cylinders can be quite heavy and need to be handled by trained, skilled personnel. And you know, if you're going to rig a cylinder and lift it up, you don't rig the strapping through the halos and try to pick it up by the halo. There are holes in the side of the halo that will give you the extra strength to do that. People that rig through the halos, they can damage the halos, interrupt the access to a lot of these vessels. I've seen them where they've actually folded up like a taco shell, if you would, and cylinders then need to get sent out and new halos welded on. Figure all the way over on the right is showing you some of the proper ways of dealing with a round base cylinder, pushing it up higher rather than, you know, using your hurting your back. So look at the table on the lower left is just showing you some really common weights, you know, to have some respect for cylinders when they're full. I mean, a 180 liter can weigh up to 800 pounds when it's full of argon, and the 265 liter goes a little over a half a ton. So how you get them up ramps, off of ramps, into customers' facilities, you need to be skilled and handle them properly. Marie, please, next slide. These figures are showing you some common configurations. So you'll have a figure 1 and 2 showing you low pressure cylinder configuration, which don't have a gas use circuit. Figure 1 is no pressure builder. Figure 2 is the same low pressure cylinder configuration, but with a pressure builder. That varies based on make and model, year of cylinder. Figure 3 and figure 4 are showing you a common Taylor-Wharton high pressure. That would be a DOT4L 200 medium pressure, and a high pressure, and actually even the VHP cylinders, showing you a combination unit, pressure builder, economizer, the way that they're plumbed in. Figure 5 is showing you when you want to operate a cylinder, this is where the pressure builder is in that particular cylinder layout. It's showing you the magenta colored handle is the pressure builder. The figure on the lower right is showing you what they call an LCCM, liquid cylinder control manifold. That would be where the pressure builder is there. Next slide, please, Marie. This is showing you a schematic of the pressure builder function. So as we had shown you in a previous slide, you have those coils, the bottom 12, 15 inches of a cylinder. You have that column of that liquid in that cylinder, and that weight of that liquid is pushing down. That you will open up that pressure builder. It'll draw the liquid up. It'll go through those coils. It'll flash into gas. That gas will feed into the regulator. The regulator has a Venturi type action to it that will create the pressure and push that pressure in the upper space of the liquid cylinder and push down on that liquid. And it will build that pressure until it reaches its preset value. And then the pressure builder will close and it will stop building pressure. On a DOT4L1 or 200, it's set to 125. On a 292, it's set to typically 300 PSI. Go ahead, Marie, next slide, please. So this is showing you gas use. So when you want gas output from a cylinder, which everybody should realize, maximum gas output out of a cylinder downhill with a tailwind on a good day is 350 cubic feet an hour. You're going to, again, the pressure builder is working in the background. It's it's doing its thing, it's building pressure in the cylinder. Now you're going to open up the gas use circuit. That column of liquid now has been pressurized, it's pushing down, it's going to draw that liquid around the coils that are soldered between the inner vessel and the outer vessel. That's going to capture heat from the ambient outside temperature, and it's going to flash that liquid into gas, and it's going to deliver a volume of gas output. Next slide, please, Marie. This is showing you the economizer function. So as I said, the pressure builder is building its pressure, and it's going to stop building pressure when it reaches its preset value. Because it's cryogenic liquid and it's inside this vessel, and there is no such thing as a perfect insulated vessel, there will be continuous pressure build up unless you're really drawing hard off of it and using it. So you have that primary relief valve that is set to the maximum pressure, but in between that pressure builder setting and the primary relief valve setting, there is, on a gas use cylinder, an economizer function. This economizer function could either be built into the regulator as a combination unit, or it could be a separate regulator function depending on the age of the cylinder and the plumbing scheme of it. And this economizer, at its preset value, will actually open, and it will deliver gas back into the gas use circuit. The whole idea of that is to try to regulate the pressure building of the cylinder and regulate it between the pressure builder set pressure and the economizer setting. So like a DOT 4L200, we'll want to regulate between 125 and 140. 292 will want to regulate between 300 and 325. Obviously, you don't use the cylinder, you turn the pressure builder off, it'll continue to build pressure. That's when the relief valve will kick in and will help normalize the pressure in the cylinder, prevent it from overpressurization. Next slide, please, Marie. So this is the liquid withdrawal schematic. So it's going to work very similar to a siphon tube in a high pressure cylinder. You've got that column of liquid in there, it's pressurized, it's pushing down. You open up the liquid withdrawal and it will draw liquid right out of the cylinder. The magenta valves are just showing you, the upper figure on the right hand side is showing you the liquid withdrawal valve location in that schematic. The bottom figure is showing you the vent, which we didn't really talk about, don't have a schematic for it, but I mean, the vent valve obviously will regulate the pressure inside the cylinder. You can, if a cylinder pressure is too high for you, you can always open up the vent in a safe location. It's not blowing in somebody's face, and vent the cylinder down. Next slide, please, Marie. Now, I mean, I could spend the whole half hour just talking about troubleshooting alone, and you know, I have an extended class that does that. But just some of the high spots here are some real common type applications. People on the figure all the way over on the left, people get asked all the time, why is this safety going off? Why is it so darn loud? Point that I want to make is that it's showing you a cross section of two different types of relief valves. The relief valve all the way over on the far left is the generate relief valve, what they call an LCV, or Ratermann calls them LPRs, liquid pressure relief valve. They are the quietest relief valve that's out on the market. They have that machined action in the poppet there that'll give you a whooshing noise, an escape noise coming out of the cylinder before the poppet opens and does a full relief. So it kind of advance notices you that it's about to relieve itself. The relief valve on the right hand part of that figure then is just showing you a normal type poppet relief that'll just bang open and relieve and then reset once it gets to its reset point. The next figure over from the left, the second figure over from the left, is showing you a dual safety configuration. That's a common problem if your company uses dual safeties. It creates a real communication challenge that you need to make sure that your end users understand how to use a dual safety, and then showing you the valve that's in the closed position, so you know which safety is going to be open, which safety is active, and which safety is inactive. So that can lead to problems where customers are saying this is constantly relieving. Well, Do you have a dual safety arrangement? Yes. Which safety is engaged? Which safety is not engaged? You can go through that question and answer period. The figures on the right are designed to just focus on frost, because people can have a tendency to freak out on frost. That's an indication of something gone wrong or a bad vacuum. The figure in the left-hand portion of that showing you what they call a barber pole effect. That would be a liquid cylinder that is heavy gas use. It's drawing hard on the gas use function of the cylinder, and those coils that are in that upper part of the cylinder that we had shown in some previous slides are drawing the ambient temperature in and vaporizing that liquid into gas, and it's frosting up the cylinder. That's perfectly normal. The cylinder, the upper part of that cylinder on the right-hand side is showing you the pressure builder coils are active. That bottom 12 to 15 inches of that cylinder is drawing that liquid around and building that pressure, and that's a frost that's appearing at the bottom. That's perfectly normal. Cylinder on the right is showing you frost that can appear after a fill. That might be a slight leak in the float on the knuckle there, but it's a frost buildup that is fairly common. Next slide, please, Marie. Some abnormal frost. The figure on the left is could be from a relief valve that got frozen open, which is not uncommon. You'd have a DOT 4L100 low pressure cylinder that has a 22 psi relief on it that just got filled with 75 or 80 psi liquid. That cylinder will need to stabilize. You could pour warm water on that and try to get the safety to reset, or it could be a broken seal in the float rod. As I said, that's the only place in that knuckle where it's connected to the inner vessel. So that could be a leak there that you could just operate the cylinder as normal, and the next time it's through, have your team pull the float rod and replace that O-ring and reset it and see if that doesn't make that go away. Figure on the right hand, it would be what I'd consider a classic vacuum broken. So with the vacuum in that annular space, it really holds the insulating value of the cylinder. When that vacuum is lost, it's as if that cylinder has that 400-degree cryogenic liquid in a pail. It is just boiling off like crazy. The cylinder will build a lot of pressure. It's liable to be clammy or frost all over like that cylinder is. The relief valve would be going off. You can open the vent in a safe direction. You can vent that cylinder down and then turn that vent off, and you can watch that pressure builder build pressure pretty quickly, and then relieve itself again, and that would be the sign of a classic vacuum. And that would conclude it. Next slide, please, Marie. So, I mean, this is who I am. I'm Ed Yeoman. As I said, I'm sales for the Northeast. You can reach out to me.